An emergency room does not serve patients in arrival order. A broken finger waits. A heart attack goes first, even if it walked in last. And look closely at what the triage desk actually asks. Nobody ever wants the median patient or an alphabetical printout of everyone in the building. The desk asks one question over and over forever. Who is most urgent right now? Treat them. Ask again. Lesson 6 called this shape a queue where the line is jumped and promised you the structure that runs it. This is that lesson. The contract is called a priority queue, and in Lesson 6's discipline, it's an ADT, a job description, not an implementation. Insert an item with a priority. Peek at the most urgent. Remove the most urgent. That's the whole menu. No ranges, no sorted walks, no where is the 7. And last lesson closed on exactly this trade. If the only question your workload ever asks is what's next, you can keep a much weaker promise than total order. And the structure that keeps it is smaller, simpler, and immune to the disease that kills naive search trees. Here is the entire promise. Every parent beats its children. In a min heap, beats means less than or equal, so every parent is at most both of its kids. Nothing about left versus right. Here's the heap this whole lesson lives in. 2 at the top, 5 and 3 below it, 9 and 7 under the 5, 8 and 4 under the 3. Check it. 2 beats 5 and 3. 5 beats 9 and 7. 3 beats 8 and 4. Every parent wins. Valid. Now notice what a search tree would never tolerate. The 9 sits on the left side. The 4 sits on the right. Smaller left, larger right is simply not a rule here. So what did weakening the invariant cost? Ask this structure. Where is the 7? And it shrugs. All it knows is that 7 is somewhere below something smaller, which is nearly everywhere. Search is order n, a full scan. Ranges, sorted walks, nearest key, gone. But look at what survived. The root beats its children. They beat theirs. The promise chains all the way down, so the root beats everything. The minimum is always at the top, readable in order 1. We gave up every question except the one the emergency room asks, and that question got the best possible answer. The heap has a second rule, and it's about shape, not values. The tree must be complete. Every level full, except maybe the last, and the last one filled left to right, no gaps. Completeness is what caches the trick Lesson 13 teased. Read the tree like text, top to bottom, left to right. Write the values into an array in that order. 2, 5, 3, 9, 7, 8, 4. Indexes 0 through 6. No pointers were stored. Instead, the family relationships become arithmetic. The children of index I live at 2i plus 1 and 2i plus 2. The parent of index I lives at I minus 1 over 2, rounded down. Round trip it on the real heap. Index 1 holds the 5. Its children should be at 3 and 4, which hold 9 and 7. Exactly the 5's children in the picture. Now backwards. Index 6 holds the 4. Its parent, 6 minus 1 over 2, rounds down to 2, which holds the 3. Correct again. It works at every index because the tree is complete. No gaps means the reading order never skips, so the positions line up with the arithmetic perfectly. Say what just happened in Lesson 2's vocabulary, because this is the payoff that lesson has been waiting 13 lessons for. This is a tree with 0 pointers. The search tree spent 2 8-byte pointers per node, 16 bytes of addresses chaperoning every value, plus a separate allocation per node scattered across memory. This stores just the values. One contiguous block. Cache warm, prefetcher friendly, a fraction of the memory, and the tree structure is never stored at all. It's computed on demand from indexes. And the second gift is bigger. Last lesson's villain was the degenerate case. Sorted input and the tree collapses into a height-end chain with every invariant intact. A heap cannot do that. Completeness is part of the definition. Every level packs full before the next begins, so n nodes always stack into height log n, rounded down. Not expected height, not amortized, not if the input is random, by construction. There is no insertion order on Earth that makes a heap lean. 1,000,000 elements is height 19, every time. The balance anxiety that consumed the back half of last lesson? Gone. Structurally. The promises only matter if the structure survives change, and the heap has exactly 2 repair moves. Here's the first. Insert a 1 into our heap. The shape rule dictates the only legal place to grow. The next free slot on the bottom level, left to right, which is simply the end of the array. Append the 1. It lands at index 7, child of the 9. Shape fixed, values broken. 9 is the 1's parent, and 9 does not beat 1, so the 1 bubbles up. Compare with the parent. Swap while the child wins. 1 versus 9. 1 wins, swap. 1 versus 5. Wins again, swap. 1 versus 2, the root. Wins, swap. Now the 1 is the root, and it stops. This is sift up. Append at the end, swap with your parent while you beat them, stop the moment you don't. Each comparison it wins on the way up is exactly the proof the invariant holds again. Worst case, it walks one path from leaf to root, and the height is log n, guaranteed. So insert is order log n, always. The second move runs the other way, and it's the one the emergency room pays for. Extract the minimum from the original heap. The answer is the root. 2. Take it. But that leaves a hole at the top, and the shape rule says a heap may only shrink at the end of the array, hence the strange move at the center of it. Take the last element, the 4, and drop it into the root's empty chair. Shape fixed. Values broken. 4 sits above 5 and 3, and it doesn't beat 3. So the 4 sinks. At each step, compare with both children and swap with the smaller one. Why the smaller? Because the smaller child is the only one fit to rule the other. Swap with the larger, and the invariant breaks immediately. 4 against 5 and 3. The smaller child is 3. 3 wins. Swap. Now 4 against its one remaining child, the 8. 4 wins. Stop. The invariant holds everywhere, and the new root is 3, the correct next minimum. This is sift down, one path from root toward a leaf, order log n. And that's the entire API. Peak, order 1. Insert, sift up, order log n. Extract min, sift down, order log n. 2 repair moves, about 10 lines each. That's the whole structure. One more trick, because production asks for it constantly. You're handed a full unsorted array, and you want a heap now. Inserting each element in sift ups costs order in log n. There's a cheaper way. Take 9, 5, 8, 2, 7, 3, 4. As an array, it's already a complete tree, only the values are wrong. So walk backwards from the last parent, sifting each node down. Index 2 holds the 8. It swaps with the 3. Index 1 holds the 5, swaps with the 2. Index 0 holds the 9, and it sinks all the way down, below the 2, below the 5. Out comes exactly the heap this lesson has been using. Why is backwards the win? Count where the nodes live. Half of all nodes are leaves. They never sink at all. A quarter sink at most 1 level, an eighth at most 2. Only one node can ever sink the full log n. Add it up and the sum telescopes. Total work under 2n swaps. Build heap is order n, flat. Every standard library's heapify does exactly this. Once you know the contract, you see it running everywhere. Start with timers. Every set timeout you have ever scheduled is a priority queue entry. Node's runtime keeps pending timers in a min heap, ordered by fire time, because the event loop only ever needs one answer. Which timer fires soonest, so it knows how long to sleep. Go's runtime keeps per scheduler timer heaps too, a slightly wider than binary flavor, same machine. Millions of pending timers, and what's next stays order 1 to read. Second, merging sorted streams. Lesson 10's external sort ended with k-sorted runs on disk that had to become one output. The tool is a min heap of size k, holding each run's head element. Extract the smallest, emit it, refill from the run it came from. Each output element costs order log k, where k is maybe 64, not log of the billion total records. The ROX DB family of storage engines runs exactly this merge during compaction, continuously. And one named a file away. Dijkstra's shortest path keeps its frontier in a priority queue and repeatedly extracts the closest node. That's a DSA pattern story. The structure will be sitting here, waiting for it. Now the marquee example. Find the 10 largest items in a stream of a billion. Sorting is off the table. In-log-in work, and holding a billion keys is 8 gigabytes before you start. The heap answer uses 10 slots. And here's the part that trips everyone the first time. You want the 10 largest, so you keep a min heap, not max, min. Because the root of a 10-element min heap is the smallest of the 10 best candidates seen so far, the weakest member of the club, the bouncer at the door. Now stream the billion items past it. A new item arrives. Compare it with the root. Once. If it can't beat the weakest member of the club, it has no business inside. Discard. Order 1. Against a top 10, that's what happens almost every time. If it does beat the root, the weakest member is out. Replace the root with a newcomer, sift down, log of 10, 3 or 4 swaps. 1 pass, 10 slots of memory. The min heap works because the question you ask a billion times is about the threshold. Who is the weakest of my current best? And that answer lives at the root, one comparison away. Leaderboards, 10 slowest queries. Anywhere biggest few out of way too many appears, this is the shape. Lesson 10's table had a row marked, wait for lesson 15. The comparison sort with guaranteed in-log-in and no extra memory. You can now build it in 2 sentences. Flip the comparison. Parent beats children now means parent is larger, a max heap, largest element at index 0. Then sort in place. Build the max heap, backwards sift downs, order in. Then repeat. Swap the root with the last element. Shrink the heap by 1. Sift the new root down. Walk 1 round. Max heap. 9, 7, 8, 2, 5, 3, 4. The maximum, 9, sits at the root, and the back of the array is exactly where a sorted array wants its maximum. So swap root and last. The 9 is parked in its final position, permanently outside the heap. The new root, 4, is wrong, so sift down. 4 against 7 and 8. The larger child, 8, wins. Swap. 4 against the 3. 4 wins. Stop. A valid max heap of 6, and the next round parks the 8 beside the 9. Swap, shrink, sift, until the heap is gone and the array is sorted, smallest to largest, in place. In rounds, each one sift down, order in, log in. Guaranteed. So heap sort has the guaranteed bound and constant space. Why isn't it simply the sort? Lesson 2 gets the final word. Watch the addresses one deep sift down touches. Index 0, then 1, then 3, then 7, then 15. Each level lives twice as far away as the last, so in a big array, nearly every step lands on a fresh cache line. A miss. Sift down commutes. Quicksort's partition streams, 2 pointers marching through adjacent memory, the exact pattern the prefetcher rewards. Same big O shape, physically cheaper steps, so quicksort usually wins on real hardware. which is why production uses heap sort exactly the way Lesson 10 promised, as insurance. Introsort, the engine inside std sort, runs quicksort while counting recursion depth. If the depth blows past about 2 log n, the pivots have gone bad, the n-squared cliff is near, and it hands the whole job to heap sort. Guaranteed n log n, no extra memory, disaster canceled. Quicksort's constants with heap sort's floor. That is, the sort your programs have been calling all along. And the course's sorting story is complete. And that closes the module. 3 structures, 3 contracts. The hash table bought order 1 lookups by destroying order entirely. The search tree kept total order and paid in pointers, height anxiety, and balancing machinery. The heap keeps exactly 1 bit of order. What's next? In a flat array, with log n guarantees by construction. The module's lesson in 1 line. Order is not free. Buy exactly as much of it as your queries need. Now step back further. Every structure in this course has assumed your data has one of 2 shapes, a sequence. Arrays, lists, stacks, queues, sorted runs. Or a hierarchy, trees, heaps. One parent above, children below. A social network is neither. A roadmap is neither. Package dependencies, microservice call graphs, the internet itself. Things pointing at things, many to many, no single parent, no first element. That shape is a graph. It's the course's final module. And the first problem is more basic than any algorithm. How do you even store one in memory? 2 classic answers, with a familiar trade between them. That's next.